I made a presentation similar to this back in 2004 at the ASC annual meeting, and so some of this is based on that presentation, and just wanted to mention that. So, again, Waterhammer analysis is essential. Pressure transients occur, pressure extremes occur during transient operations. Easy is sort of based on the idea that we can view transients in a very intuitive manner based on pressure wave movements, and I'm going to expand on that. And efficient is that we can make these calculations efficiently so we can handle networks of all sizes, particularly large water distribution systems. Some of the traditional techniques are not efficient enough to handle these large systems. So what is a pressure surge? This screen shows a plot, and basically the plot's indicating that you're at steady state and some event occurs in your piping system. It might be a blowout of a pipe as shown in the picture, but more commonly it would be turning a pump on or off, or opening a valve or closing a valve. And once that occurs, you start getting pressure fluctuations and flow fluctuations in your system, and you'll have a period of transient pressures and flows, and then finally another steady state, which would be the steady state that would occur based on the condition that caused the transient. For example, if a pump came on, it would be the steady state with that pump running. So this is basically how we describe the surge. We have some slides here, and Pulsco is a surge tank company that I got these slides from because they were very effective, and I think someone today is attending the meeting or webinar that's from Pulsco. I saw them on the list, so we do appreciate being able to use these. But what we are showing here is that we're representing the transient conditions by an engine, which represents a pump in a system, and the cars, which represent the water. And the first slide at the top here shows one of the most common, or probably the most common problem of concern, and that is if the pump fails, what happens? And so it's showing here the pumps failed, but the cars have a lot of inertia. The water has a lot of inertia, and it keeps moving, and it can actually separate from the water column can separate, and then due to gravity and other forces, it can reaccelerate, change direction, come back, and impact on the pump and cause a very high pressure surge. So that's the probably the single most situation of concern when we look at transient analysis. When you start up a pump, because of the inertia of the water, the engine will work harder than it would normally work under steady state conditions, and you can get a pressure surge or a spike in pressure at the beginning of the event when the pump turns on. So that's a second situation that commonly causes pressure surges in systems. This represents, the real crux of the matter is that anytime you have a rapid change in the velocity of a water column from any event, a valve closing, a check valve closing, a pump tripping, and the upstream, if it's a booster pump, the upstream flow is retarded very quickly. Anytime you have a rapid change in velocity, you're going to get a pressure spike, and that's so these are the situations that will cause the most concern in when you're looking at your operation of your piping systems. So why do we want to do a surge analysis? Well, this slide shows the reasons that I've outlined. The pressure extremes always occur during a period of transient flow, the highest and lowest pressures. And clearly, when that happens, you can exceed design limits. You can have cavitation occur. Cavitation is when the water vaporizes, and then it can collapse, and the water will be traveling rapidly when the vapor pocket collapses and cause a pressure spike. So the high pressures break pipes. Clearly, in water distribution systems, the pressure surges in the system are causing additional pipe breakage over what you would get if you could mitigate those pressure transients. Low pressure transients cause damage to seals, and that will increase your leakage. And also low pressure transients can cause a health risk. I'm going to expand on that a little bit, but that's a very serious consideration for drinking water systems. Finally, we need to do a surge analysis so we can evaluate surge protection schemes. Now I'm going to go through just step you through a quick example here where we are going to use the Surge 2010 software to look at what happens when a pump trips in a system or where the pump is shut down in a controlled manner. So in this particular system, which I'll move on to here, we have a couple elevated tanks in the system and a pump. So when the pump turns off, the elevated tanks take over the pressurization of the system, or they provide all the pressurization. When the pump's on, the pressurization could be a combination of the pumps and the tanks. So when the pump is on, the lowest pressure in the system is shown up here, circled in red, around 54 psi. When we turn the pumps off, we're looking at steady state. We're down to just about 50 psi. So there's almost an insignificant difference in the operation of the system. But the question here is what happens following turning off the pumps, and what happens if the pump trips, which means that you lose power to it and you can't control the shutdown. This next slide shows sort of a controlled shutdown. The pressure starts at around 54 psi. It fluctuates just a few psi and ends up down at 49 psi. But this was a controlled pump shutdown. It didn't occur too rapidly, so there's no real transient problems. But if we trip the pump, and by pump trip I mean the power goes out, the pump runs down very quickly, and within the software we have tools to calculate the rundown based on the inertia dynamics of the pump and motor. But when this happens, you're seeing again the pressure at this node where the pressure was 54 psi. It drops all the way down, and if you see this bottoming out shown here in the blue circle, that means cavitation has occurred. Now your water column will separate, and you've got very low pressure, minus 14 psi, minus 30 feet of head. And you've got overhead tanks in there that have a couple hundred feet of head. So you're going to get the water column separating due to the inertia, but it's going to collapse and cause a pressure spike. So this is the situation that we see when there's an uncontrolled pump shutdown. What can you do about that? I'm going to talk a little bit more about surge protection. But if you had a surge tank, which is shown over here in the left, when the pump trips, the pressure drops, and the surge tank is really basically you have a storage of water under pressure. And so when the pressure in the pump in the pipe falls, the surge tank can provide water. And these events occur very quickly. So basically, we need to provide water until we get reflections back from the overhead tanks and so on, maybe only a few seconds. So the surge tank will provide water, and so this plot at the lower part shows the results when you have a surge tank in the system, and the results that I showed you a minute ago when there was no surge tank. And with the surge tank, you can control even the pump trip. And of course, there are other ways to do this, but without putting in a surge tank or providing other forms of surge protection, you would get some low pressures. And the next slide here shows all the pressures that went subatmospheric. Now, in a drinking water system, subatmospheric pressures are really very dangerous to the public health, because anytime you have a subatmospheric pressure, any leaks become basically the pathway for dirty water with pathogens in it to intrude back into the system. So you really should never allow pressures to drop below maybe 20 psi positive in a drinking water system. We'll talk a little bit more about this, but this poses a serious risk problem. It's been studied by EPA and by the American Water Works Association, and it's clearly a problem that is of concern. Here's another example of a transient and what we might be able to do about it. In this particular example, we're going to close this valve. And one reason for showing this example is that the characteristics of the valve become very important in transient flow. So we're going to close this valve, and when we do that, the pump will pump water only to this elevated reservoir, where prior to closing it, it's going through to the reservoir and to the valve. So we intuitively would know if we close that valve that this total amount of water that's being pumped would decrease a little bit, and the pump would go back on its curve and produce a little higher head. Now, different types of valves, we're going to look at closing a butterfly valve, and this plot shows basically how the effective area and really the effective valve coefficient varies with the stroke. In other words, at 50% of the stroke, the butterfly valve is only about 25% open, whereas the gate valve is still about 75% open. Now, what that means is that when the very last part of the stroke, you're going to reduce the velocity much quicker with a gate valve because it hasn't closed. It's only 25% closed, and so there's still a lot of flow. So this next plot shows what would happen if we close this butterfly valve. And what we intuitively thought would happen, you start at a certain pressure, you close the valve, you end up, this is the pump discharge head, at a little higher pressure and a little lower flow rate, which is what we would expect. But if we do the same operation with a gate valve, this is what we get. And clearly this is a serious problem. There's cavitation occurring, pressure spikes, and that's because, again, there was a much higher velocity at the very end of the stroke, and the associated pressure spike was larger and caused all this problem. So the characteristics of the valve can be a very important consideration in transient flow. If you put a surge tank in here, again, when the valve shuts the surge tank, the water can flow into the surge tank and compress the air, and this is one way that we could mitigate this serious pressure transient that we saw. And the next slide just shows the effects. This upper slide here shows with no surge tank, the pressure goes up, cuts down to cavitation. With the surge tank, it's a very smooth transition. So there are ways that we can control these pressure spikes or pressure surges, and we'll talk a little bit more about that as we go through. Now, here's a caution. I mean, this is one reason that you need to do surge modeling, is that you can add a device, and it actually can make the situation worse. And this example here is talking about an air vacuum valve, which is a device that pulls air into the system when you have a low pressure, subatmospheric pressure, and then when the pressure starts building up again, it expels the air. Well, if you expel the air through a larger orifice, some of these devices have maybe even a 6-inch orifice that they bring it in and expel it, you can get a pretty big pressure spike. And this is basically the same thing that you would get if you had a cavity collapse. It's due to the water accelerating and impacting on itself and causing a huge pressure spike. A few years ago, they were having a problem in the Pittsburgh water system. Every time they had a power outage, they would rupture a pipe, and it turned out that the problem was due to this air slam from an air valve, and the solution was to put in a smaller orifice when you allow for the air to come out, a 2-stage air valve. And we're showing here that if this were, say, a 3-inch inlet and outlet orifice, we might get 100 psi pressure spike. But if we had a 1-inch outlet orifice, it would allow the water column to collapse more slowly and limit the pressure spike. Well, one thing I certainly want to stress in this is that vapor cavities are a serious cause of pressure spikes and need to be avoided. And I went back to the dictionary just to see what they'd say about the cavitation, and I thought the definition wasn't too bad. It says, as shown down here at the bottom of the slide, the rapid formation and collapse of vapor pockets in regions of very low pressure are frequent cause of serious structural damage. Well, that's basically true. The next slide I want to give you an idea why this can be a pretty serious problem. Now, this is sort of the classic problem that, if you want to avoid, if you're looking at piping and you have a situation where you're pumping into a pipeline where there's a reservoir or a tank that's elevated, this is always a situation of concern, because if you trip your pump, your water, if it does cavitate, you've got a substantial head to collapse the cavity. So what this is showing here, the pump is pumping up to the reservoir, and the pump trips, so the pump starts running down the other direction or slowing down. But the water can continue to move, and what happens when this water moves is the pressure drops, and if it drops all the way to vapor pressure, you form a vapor cavity, and the cavity grows. But now, because there's low pressure here and high pressure in the tank, the cavity slows down and then starts accelerating back toward the pump. And you get this. I don't think you can hear that bang, but there's been many a case where you've ended up with a serious problem, a rupture of a pipeline, a ruining of pumps because of this. Now, I want to show you this again with some numbers in the next slide. Here, let's say we're pumping up from a pump, we're pumping to a 100-foot elevation change. And the pump's developing, let's say, 130 feet ahead. So 30 feet of head are overcoming friction. The 100 feet of head is just overcoming the elevation change. So this water is moving at a certain velocity, maybe 5 feet per second, and it's expending 30 feet of head. Now you trip the pump, and the pressure becomes minus 30 here. Now you have this 100 feet of head, so now going in the opposite direction, you have 130 feet of head, which is collapsing the water column. Well, 130 feet of head can move a water column considerably faster than 30 feet. So if you may have 5 feet per second of velocity initially you may have 10 feet per second of velocity at the time it collapses. And keep in mind, we'll talk about this a little bit later, but the pressure spike, or the pressures, you can roughly estimate the pressure increase due to deceleration. If you had like a ductile iron pipe or something, it's on the order of 50 to 60 psi for every foot per second. So if you had 10 feet per second that were collapsing, the velocity, you could have a pressure spike of 5 to 600 psi. So it's a very serious situation. Well, now I want to talk a little bit about the study that AWARP did about low-pressure surges in water distribution systems and how we use modeling to aid in this study. And I'll go through this fairly quickly, but here's a water system. It's actually Davenport, Iowa. And what they did was they had high-speed recorders, and they recorded pressures for a period of months. And the next slide will show you where the recorders were. Right down here was the main pumping station. The Mississippi River's down around here. And there were all these different recorders, and the one that's circled here, when they did finally record a pump trip, and this was the location that had the lowest pressure in the system. So they were trying to basically record an event that and see whether there was a possibility of low pressures in the system. So this next slide shows the actual recording, and this was the event that occurred at 8:32 a.m. in 2001, and the pressure dropped all the way from 55 down to below 10 psi. Now we modeled that system with Surge 2000, and this is the model predictions, and they're very similar. I mean, so we realized, or we could verify that our model was pretty accurate. The next slide even shows more evidence. It shows how far the pressure dropped at the different sites. Now, some sites, the pressure only dropped, like in site number 2, 8 psi. But in site number 3 was the one where it dropped the most. But the recorded pressure drops and the predicted pressure drops were very similar. So we had a good prediction of the whole system. Now, what that allowed us to do was to go in and predict where pressures would go subatmospheric. So this next slide shows that even though there is nowhere in the system, or nowhere where we recorded pressures that we went below about 10 psi, there were many, many locations in the system where there were negative pressures. And this is, really an unacceptable situation. We did another study, and this happened to be Lexington, Kentucky, where I was teaching at the university. And again, they have a pump station down here by the river. They had only one recording device over in this area, but they recorded a power outage pump trip, and they had actually recording at the pump station and in the system. And they recorded a pressure drop all the way down to almost 0 psi. Now, this was a fairly large system, and we went in and modeled that system and did the same sort of analysis where we showed that even though the pressure dropped only to 10 psi, all these locations experienced subatmospheric pressure. And that means that anytime you had a leak in the system, you would have been intruding dirty water. You should have issued a boil water alert. Well, how do we do surge analysis? This is sort of the first part. It's essential to do. The second part is how do we do it? And the basic equations are pretty nasty. They're partial differential equations. There's a continuity and a momentum equation. And only the best mathematician could even hope to solve these. And I did work with some mathematicians at Kentucky, and they solved some very simple problems. The method of characteristics is a numerical method that's been around quite a while, which is basically a technique to convert these partial differential equations to ordinary differential equations and solve them. And finally, there's a method that we developed called the wave method or wave characteristic method, which is a numerical solution based on the concept of pressure wave movements in the system. So I want to talk a little bit about, these approaches. Now, again, the method of characteristics is you basically you update pressure and flow at some point in a pipeline based on the pressure and flow at adjacent points within the pipeline one time increment ago. And for transient analysis, these are very small time increments. A hundredth of a second would be a fairly large time increment. So every hundredth of a second, you're making these calculations in your system. And this is all sort of based on the mathematics. The partial differential equations at the top are rewritten as ordinary differential equations, and you go through this process. And as the poor guy down here at the bottom, it's not simple. It's not easy, and it's a mathematical procedure, and you end up with these characteristic lines, and it's a mathematical procedure for solving these partial differential equations, and so that's not easy. And so if I say we're talking about this not being difficult, it's obviously not this method. Now, the wave analysis method, I was fortunate enough in back at Carnegie Mellon when I was studying that I had a very brilliant professor who got up and talked about transient flow. He said, well, you close a valve, you generate a pressure wave, it travels at sonic speed. When it gets to another valve or a pump or a junction, it will be reflected and transmitted through that. And that's basically all that I had learned about it. I went on and did my PhD work looking at pressure wave action at junctions, but I was looking at it strictly from a viewpoint of pressure waves being generated and moving through the system. This equation up here, called the Joukowsky equation, named for a Russian engineer that developed it over 100 years ago, just says that the pressure change, and this is in feet head, is wave speed over g times the velocity change. Now, wave speed is generally, if you have metal pipes, ductile iron cast, is over around 4,000 feet per second. So C over G is a pretty large number, like 100, 125. PVC, it would be much less. But that means the pressure change in feet of head would be 100 to 125 times the velocity change. So this starts giving you an idea of where, what the severity of these pressure surges will be. So the analysis based on pressure wave motion or pressure waves moving through the line, the wave method, is that pressure waves are generated at the source of a disturbance, which normally will be valves opening and closing or pumps starting and stopping. They transmit down the pipelines at sonic speed. If they impinge upon a discontinuity such as a junction or another component, a pump, a valve, or even a surge tank, they'll be modified, and we can do a fairly simple analysis to show that. So, this sort of takes this another step that I want to look at, but the wave method, if we close the valve here, we would generate a pressure wave, and it would travel down toward the junction. When it got to the junction, it would be transmitted through each leg and reflected back. Now, this slide is showing sequences of steps. So I start up here at the top, the valve shuts, a wave is generated. It travels, say, 4,000 feet per second. So this is 1,000 feet long. In a quarter of a second, it's down here to the junction. Now, when a wave hits a junction, it transmits down each of the other legs and reflects back in the leg that it came down in. I've got timing on these slides. I guess it's to keep me from going on too slowly here. But the pressure waves then will go down, and this one will hit the pump, and this will go back and hit the valve that will close, and so on. Now I have an animation that sort of shows you this too. Let me try to play this. Okay, so I'm going to close this valve, generate a pressure wave, and this is going to sort of show what happens. Let's just play this thing and take a look at it. So the wave travels to the junction, becomes 3 waves. Now, the wave hits the pump because it's short of light, becomes 3 waves. These waves basically pass each other. They both change the velocity and the pressure, but they don't affect each other, so they can travel on down. So that's that's basically how the analysis is done. Now, as I said, did my PhD work on the transmission of the waves at a junction and the reflection, because I didn't quite believe the equations, but they turned out to be perfectly good. So, this is relatively easy. We're saying we're going to formulate this solution using this Joukowsky equation that says that the pressure change is C over G times the velocity change, and that pressure waves will start at a point where the pump changes speed or trips, or a valve opens or closes, or a hydrant opens, and they're going to travel at sonic speed, and every time the wave travels by, it changes the velocity by amount delta V and the pressure by a corresponding amount delta H, where the relationship is given by this. So intuitively, it's a very simple process, and we can estimate the surge potential based on this equation. And this is a very useful exercise to go through. In other words, if I had a pump pumping at a velocity, let's say, of 2 meters or around 6 feet per second in a ductile iron pipeline where the wave speed's 4,000, I can say if the pump trips, the maximum downsurge ought to be around this much, 750 feet, which would be over 300 psi. If I close the valve at the other end instead of tripping the pump, again, the deceleration of the water would be from 6 feet down to 0, and it would cause the same sort of pressure increase. So you could get a downsurge or an upsurge and estimate that. Now that's way oversimplified, but I often get folks calling and saying, do I have a pump trip problem? And you can sort of take a quick cut at that by looking at the velocity. If the velocity, initial velocity times C over G, that pressure change is less than the pressure at the pump, then you're probably not going to have a problem. In other words, if you're generating 300 psi, but you're only predicting a 200 psi drop for, if that velocity is decelerated, then you're probably going to be fine. But if you have a 200 psi discharge pressure and the velocity is such that you're going to get a 300 psi pressure drop, there's a very good chance that you'll be facing a situation where cavitation would occur. The pressure wave speed, this becomes a very important part of surge analysis. And when you do a surge analysis and you have a steady state model, really the principal additional data you need is just the wave speed in the various different types of pipe. So this is a chart that just shows you the wave speed, and what this is showing is that when the diameter over the thickness, if this number gets larger, which means it's a thinner wall pipe, it reduces the wave speed. In fact, the equation here says that the wave speed is the elastic modulus of the liquid over density, and that's the wave speed in just a pure liquid. In water, that's around 4,700 feet per second. But then it's modified by this term in the denominator, which is 1 times some restraint coefficient times the elastic modulus of fluid, diameter of the pipe, elastic modulus of the conduit, and the thickness of the pipe. So generally, we have tools, but you need to make that calculation. Generally, the lower the wave speed, the less surge problems you're going to have, because, again, keep in mind the pressure change is wave speed over G times the velocity change. So lower wave speeds, like in PVC pipe, shown here, are going to result in lower pressure surges for the same change in velocity. Well, I mean, can you actually get a good solution this way? So, I mean, how does it work? So we're looking at comparing the solutions we get using this method based on the movement of pressure waves with the rigorous method of characteristics method. Before we get into that, to do a general surge analysis, we need to be able to handle what happens when pressure waves hit a component such as a pump or a valve, what happens when they hit a junction, what happens when they hit a device that will inject flow in and out of the system like a surge control device, and what's the effect of friction. When a pressure wave goes down a pipeline, say a 1,000-foot pipeline, it will be slightly attenuated, and there'll be a very small reflected wave. So that's what you need to do a general analysis, is just a routine to handle these four situations. Now let me sort of expand, since pressure waves at junctions was sort of has a special place for me because I worked on it on my PhD. But the equation, if you have a pressure wave approaching a junction, the transmission coefficient, when you multiply the wave by that, it will tell you how much transmits down each leg. And it's twice the area over the wave speed of the incoming pipe divided by the sum of all the areas. So that means if I had, say, a 6-inch line going into two 6-inch lines, this number would be 2/3. So if I had a pressure wave of 100 psi, I'd get a wave of 66 2/3 going down each leg and a reflection of -33. So that's, I mean, it's a simple thing. If you have a wave and it hits a dead end, there'll be a reflection of +1. Now that's, down here, that starts raising some eyebrows, because if I have a wave of 100 psi, it will increase the pressure by 100 as it goes down the line. If it reflects off a dead end, it will increase it again by 100. So you'll double the effect of that wave. Whereas at an open end, you get a negative reflection. So if it increases it by 100, the reflected wave will take it back to its original value, which is what the reservoir will do. Well, we have some animations here, and I just want to sort of show you a couple of these. So here's, say, a 6-inch line going into a 12-inch line. Now, because the area of the incoming pipe is small compared to the total of the areas, we're not going to get that much of an effect. So here's a pressure wave of, say, 100 feet coming down the line. The transmission coefficient is only 0.22. In other words, twice the area of this over and thinking the same wave speed approximately. So twice the area of a 6-inch line over the area of 2 12s and a 6 gives you 0.22. So that's, and a lot of people sort of have the concept that when you're in a distribution system, pressure waves start going through the system, they get transmitted at junctions, that you're going to reduce the effect. Well, that's true if you're going from small pipes into large pipes. However, most of the time, if we start at a pump station, we have larger pipes. So let's look at this. Now, this is a 12-inch line going into a 6-inch line. Now, twice the area of the 12 over the wave speed divided by the sum of all these three areas is greater than 1. So let's see what happens here. A 100-foot wave becomes 133 feet. So now we're not so sure. We go from a 12-inch line into a 6-inch line. We're actually putting a larger pressure wave into the 6-inch line. Well, if that's not bad enough, let's look at this next situation. Here we have a dead end down here. It didn't show up perfectly, but this is a dead end. Now the wave is going to come down and get reflected off the dead end. So here comes your 100-foot wave, becomes 133 feet. The pressure at the dead end now goes up by 266 feet. So we had a 100-foot wave, say 650 psi or 40 psi, and now we're looking at a 266 foot increase in pressure. So dead ends and pipes, large pipes going into small pipes are very significant. So that that sort of is at odds with the idea that you can get rid of all your smaller pipes when you do surge analysis. Because if you're going from 12 into a 6 and a 6 into a 3, you could end up getting some very high pressures in those smaller pipelines. Well, the next question is how does this work, using this wave method as opposed to the more complicated method of characteristics? And obviously we can't do exact solutions. Well, we published a paper. Dr. Lingretti is a co-worker of mine, cohort, has a company over in India. Dr. Boulos is president of MWH Soft, which yesterday said they were changing their name. But that's a very widely known company. And Brian Carney is a professor, Dr. Carney at Toronto. So these people were involved in this. Well, the first thing, over 20 years ago, we worked with a mathematician and published a paper where we compared an exact solution, a method characteristic solution, and a wave method solution. And down here at the bottom, I'm sort of expanding, but at this time, here was the pressure and then the flow predicted by one method, by the other method, and by the third method. They were identical. And, at first that seemed sort of strange. Here's these numerical methods giving identical solutions to exact methods, but the mathematician explained that the solution of the wave equations is sort of a stepwise, it's solved in a stepwise fashion, and so these numerical solutions are basically identical to the exact solution. So that was very encouraging. More recently, we've just compared some software. Dr. Carney had some software that's fairly widely used based on the method of characteristics. So we went in and started comparing some of these. This first problem was in a text by Streeter and Wiley. Now, that's been often regarded as the classic Waterhammer textbook. And so in this problem, they closed a valve here in 0.6 of a second, and they looked at the pressure at this location. And so we went in and we did a solution using the software based on method of characteristics and based on the wave method. And here are solutions. These are two solutions. Now, so the first thing you might note is there's pretty odd wave shapes. But the second thing that you really would note is that there's essentially no difference in the two solutions. The only difference would be how friction is handled. Because in the method of characteristics, you're solving at interior points all along the pipeline. So the friction gets handled maybe at 10 different interior locations, whereas with the wave method, we just make one calculation for each pressure wave to account for the effects of friction. Well, we carried this this is the solution using Dr. Carney's software and superimposing it on the method, the wave method solution. And this goes on. Here's another problem. And the numbers that we're showing here, though, are the number of calculations that it took to carry out this calculation. It took over 1 million with the method of characteristics and under 100,000 with the wave method. But again, these odd wave shapes are reproduced exactly. And here's a final example, which is an EPANet problem. And again, a pump was shut down, and solutions are identical, which they should be. I mean, there's only one correct solution. But we have had folks, talk about whether this is an approximate method. My software has a mind of its own. Here's a comparison of that last solution. Gee whiz. Okay, so let's do a closer look at the difference between these approaches. The wave method, you calculate at each component. So I calculate in this little problem, I'm calculating at the reservoir, the pump, and the junction here and here, each time step. So I make a calculation for each of those and one for each of the pipes. So I'm making 9 calculations. The method of characteristics, however, you have to do interior calculations, and you might do them, say, at every 100 foot. Now that might work fine, but that would require 34 calculations for each time step. But if you had some short pipelines, you might have to do it even at a closer interval of distance. We might have to do it at every 10 feet, and that would be 290 interior points. So we're going to be making at minimum 34 calculations instead of 9, and as many as 294. So that's starts becoming a serious problem when you look at water distribution systems that are fairly complex. These systems we looked at before, I'm just roughly showing you why you should care if this happens, and it just basically verifies the fact that you would quickly get into a situation with the method of characteristics where you couldn't really handle the problems. Now, why do they make the interior calculations? I mean, that's it's the way the numerical method came out, but what it accomplishes, it transmits the disturbances. So if we have a pressure wave at one end of a pipeline and there's 20 interior points, 20 time steps later it reaches the other end. But we know exactly how long it takes, so we don't really need to do that. And to handle the friction, and as I pointed out on these solutions, if we attenuate the pressure wave by one calculation, that there's really no distinguishable difference between doing that and doing a whole lot of calculations. I went through another exercise here where we can add, of course, with the wave method, you can put in as many nodes as you want, whereas with the method of characteristics, you must put in interior nodes. So I went through a problem like this where there was only 15 nodes in the system, but we added interior nodes up to one every 50 feet. And this just basically shows the solutions, and they're essentially the same. So you don't gain any computational advantage by making all these extra calculations. It's just overhead, and so it just allows the method, the wave method, to be a much more efficient algorithm for doing these calculations. Now here's sort of a case study. In fact, this is a fairly recent. This is a city in Indiana, I think, and they were putting in new pump stations, and they were doing a surge analysis to see if they needed to protect them, and I think they ended up putting in some fairly large surge tanks to protect them. This is just an expansion. This is a Surge 2000 program, just looking at a zoom in at the pump station. So these 4 pumps were going to trip, and we wanted to look at the analysis. This was just the initial steady state, showing the pressures here around 100, and down here they're more like 60. Now what I think I want to do here is to actually bring up this problem. Here it is within Surge 2000. Now this system has, if I go in here and look at it, it has 4,000 pipes, 3,200 nodes, 6 tanks, 20 pumps, and so on. It's a fairly good-sized system, not enormous, but fairly good size. And I want to do an analysis here to just show you how this analysis proceeds with the wave method. So I'm going in here, it's going through doing a steady state, and then it's going to start doing the surge calculation, and it will show you a plot when it starts doing the surge calculation. Now this is a 122nd calculation on this 4,000 pipe system. And so, that's pretty fast. And when you're done, you can go in here. This was the location that we were showing on the screen. I can go up and look at any location. There's a location up there where the pressure dropped from 80 down to almost 0. Here's a location over here near a tank, way far away, where the pressure only dropped from 58 down to 54. I can go to more of a scale here where this is 10 psi to 100, and there's very little pressure change. So once we're done here, we can look at any place in the system and see what the pressures are and go over the results thoroughly. I see I'm running out of time, but I'm almost done, so let's complete this. So basically, we could run the results. Here's with the pump trip. Here's with the surge tanks. So we size surge tanks, and that's an ongoing project. Without the surge tanks, when we did the pump trip, all these locations went subatmospheric. So it was pretty clear that we needed to have some sort of protection in this system. Now, very recently, I was working with some engineers, and one engineer had this 15,000 pipe model that they were trying to do a surge analysis on. And they were using a method characteristics program, and it crashed and wouldn't run. And the support that they got, all they said is they had to simplify the model. So they reduced it to 7,500 pipes, and they ran a pump trip, and it took 4 hours of computation. We've set up the same problem, took the 15,000 pipe model from EPANet, converted it, ran it, and it ran in less than 2 minutes. So it's something that the point we're trying to get across is that if you're going to do any modeling of large systems, you better have an efficient tool to do it with. Finally, I want to talk a little bit about protection. How you protect your systems, and there's really this slide shows that to prevent low pressures, you either admit water or air to the system. Whereas the pressure starts dropping, you have a surge tank, it puts air into the system, or you have an air valve and it pulls air. The surge tank puts water into the system, the air valve puts air into the system. If you're trying to protect against high pressures, you expel water or from the system. So a pressure relief valve would do that. Now there's also active surge control and passive. Now active tries to prevent the surge from happening. And the surge tank would do that. The surge tank will prevent the pressure from dropping down to cavitation or prevent the pressure from spiking up. Whereas passive surge control responds to the situation. For example, a pressure relief valve. If you set it at 200 psi, the pressure is going to go up to 200, and then it will relieve it. This slide is from my English colleague, Dr. Thorley, so it has some strange notations like suction ponds and so on. But this shows this classic problem where you're pumping up to an elevated tank and the different things you could do to protect against a pump trip. And just quickly going over these are all devices that we model in our software. You can increase the inertia of the pump, put a flywheel on. Now that may sound strange, but people do that. And what that does, of course, is when the power goes out, the pump runs down much more slowly, and therefore you don't get this very severe pressure drop. You can also put a bypass line in, and these work very well for booster pumps, because when you trip the pump, the pressure on the suction side will go up because you're decelerating that water, and on the suction and on the discharge side it goes down. But if you have a considerable pipeline on your suction side, like you would for a booster pump, you can bypass water, which will prevent the high pressure on the suction side and help overcome the low pressure on the discharge side. Now, surge tanks. You have compressor tanks, bladder tanks. They're very similar. They're air over water. The only difference is the air would be in a bladder instead of just directly over the water in a bladder tank. So these devices are available and work well. So a couple passive devices, a pressure relief valve. So if the pressure goes up, this valve can open up and relieve and keep it from going over, say, 200 psi or something. A surge anticipation valve is a valve that is set with a timing cycle that senses when there's a large drop in pressure due to a pump trip. It senses that and goes through a cycle where it will be open when the positive wave comes back from the reservoir downstreams. And again, we need to talk about these in some detail when you're using the software, but these are all different devices. There's what we call a discharge tank, which is like an open surge tank. Now, you can't put an open surge tank here, for example, because it would have to be as high as the steady-state hydraulic grade line plus fluctuations. So if you had 200 feet of head, you'd have to have a 200-foot high open surge tank. But you could put one out here where the normal hydraulic grade is 20 or 30 feet. Here is what we call a discharge tank or a feed tank, where the tank is equipped with a check valve. So if the pressure starts dropping in here, and say this is set at 10 feet, when it drops to 10 feet, water will come in and relieve or stop the pressure from dropping even lower. And of course, air vacuum valves are very common devices which are used, which emit air into the system and then release it, hopefully in a controlled manner where you won't create these air spikes. Well, finally, this is the last thing I'm going to do today is we have some very interesting tools for reviewing the results with and without surge protection. Here's a system where, say, this is our classic system. We're pumping up here to an elevated tank, and the pump trips and sends a pressure surge down the line. So we can look at what happens when there's no protection in the system, when there's air valves in the system, when there's a surge tank in the system. Now, in the last year or so, we've added some animation for profiles that really would be very, very useful, I think, for some presentations. So we wanted to show you this. And I'm going to get out of this in order to do that. Now, here's one of the animations, and what's going to happen here is this is just showing the pump. Here's a check valve, and then it's pumping up this pipeline. It's sort of animating the flow. When we trip the pump, you'll see the pressure drop very quickly, the check valve close, and you'll see what happens in this system. Now here, check valve closes. This is cavitation. Feeding cavitation. If you watch, when the cavity collapses, you get pressure spikes. Not a good situation, but very common. So in this particular problem, we had no surge protection. We got lots of cavitation. This could be acceptable in some, like a dirty water pipeline, raw water or something. But if the pipes could withstand the full cavitation. Now here's one where we have air valves. Now when this closes, you'll see the pressure surge goes down, and you'll see these air valves activate, and you won't see cavitation. But something does happen that I want to point out here. So here we go. Now you see there is some cavitation here, but nothing here. The air has come in, Now watch here, the air goes out and you get a bang. And once that bang happens, you start getting cavitation. Now these were air valves that weren't releasing the air slowly enough. Let me replay that thing. So what happens, of course, initially they're quite effective. They're pulling air in when the wave goes by. But as I say, if you watch that one, you'll see when the air is expelled, you got a pretty big spike, and that now it starts causing problems throughout the system. Well, finally, here's a surge tank. Now, when the valve closes, you'll see the air push the water into the system, and it keeps the pressure from going down, and the air is going into the system, and you get the pressure confined to, this is the low pressure line, no negative pressures, everything works just great. So these animations would be very useful for looking at the effects of adding certain types of surge protection. And these are particularly good for a single pipeline. Well, there's just a few conclusions here that, pressure surges create problems. Low pressures in drinking water systems are really a bad thing. The wave method provides accurate solutions and efficient solutions. And also it provides you an intuitive basis for looking at what might happen. If you have dead-end pipes and you have larger pipes going into smaller pipes with pressure waves coming in, you may very well have a problem. You can get more frequent pipe breaks, pump failures, broken seals, all these bad things can happen. And finally, you should do pressure surge modeling. It's essential for safe and reliable design. And again, I mentioned earlier that you can get a PDF of this slide presentation, and the girls who were so kind at the beginning will let you know how to do that or send you an email.
Okay, Dr. Wood, we've got a few questions.
All right.
Are you ready for them? Okay.
I think so.
Okay, the first one.
All right, here we go, yes.
Bonnie. His question is, what is the procedure for controlled shutdown of pumps? If we hit the stop button on the motor starter, is it going to be any different than a sudden power outage? So can we handle it like a trip, I guess is the question.
Well, yeah, I think that's right, unless they have a procedure. I mean, a controlled shutdown might be done more through valves than the pump. But I would guess that if you push a shut button, unless you have one of these soft starts or soft shutdowns, you're going to get like a trip. Yes.
Okay. I might add that you can shut the pump down over time as well.
Yes.
Okay. Next question. Please explain the effect of higher altitudes on column separation or cavitation. Should the vapor pressure of the water, the property in the model, be adjusted to account for lower atmospheric pressure?
The answer to that is yes. We have a default value that's based on standard conditions, but you certainly should be putting in a different value for the cavitation head at high altitudes. So that is critical information.
Okay. And that is in the system data simulation specs, right?
In the system data, there's yes.
Okay. The next question, again from Jeffrey Rosalind. Have you experienced the valve manufacturer's tables and nomographs for sizing surge anticipation valves, SAVs, or pressure relief valves based on pipeline size and flow rate to be accurate, or should a surge analysis still be run to verify sizing and timing on the valves? Did you understand that?
Yeah, I do, and I think
okay.
The timing is based on should be based on a surge analysis. I would be pretty uncomfortable not doing a surge analysis if I was using a surge anticipation valve. They certainly need to know how long it's going to take for the major negative or positive reflections to come back, because the timing is all based on getting the valve operating when the high pressure returns are expected to occur. So I would certainly think that I would want to see a surge analysis done at least by the people who are providing the valve.
Okay. Are there any situations where you would prefer the MOC over the wave method?
No, I mean there are really none, and you may think I'm biased, but in the MOC you have to have these internal nodes. In the wave method, you can put nodes wherever you want, so there's no disadvantage of the wave method. I mean, there's you can if you're concerned. Now, the argument we have heard from folks that are concerned about the MOC going away is that, well, you might miss something. And if you have a transmission line that's a rising main, we certainly would put nodes primarily at the high and low points, but we don't recommend you go over 1,000 or 2,000 feet without putting a node in. So you put some nodes in. You just don't have to put them in every 10 or 15 feet, which you would if you wanted to model short pipes, say in the pump station. You're going to have to put in an awful lot of internal nodes to cover that requirement. So there is I see no advantage other than you're forcing the solution to be carried out at many intermediate points. The modeler certainly should be able to decide whether he needs additional points in the system.
Okay, from Steve Roy, to expand on Jeffrey's first question, if your software does not already contain manufacturer's valve tables, can information be added to simulate this equipment?
Yes, we have some standard valves in there, gate, butterfly, and so on. Using some typical tables. It's very easy to go in. The way we do that is we put in a value for every 10% of the stem motion. We put in the CV ratio, and you can name the valve whatever descriptive name you want. So it's quite a simple process. And now when you add a valve to your system, there's a drop-down list that will include our standard valves and any valves that you have added to that list.
Okay. Can a check valve be placed anywhere in the system?
Yes, a check valve can be placed anywhere in the system. Check valves are modeled as an active valve, just a regular valve with a closing time for the check valve and a resistance for the check valve. And the valve itself has a directional symbol that tells you which direction the flow is allowed. But they can be anywhere in the system.
Okay, this is
They can also be incorporated with a pump. I mean, you don't have to put a separate check valve in. You can indicate that the pump has a check valve.
Okay, from Sean Wang, what is the difference between the MOC and WCM in terms of friction effect?
Well, all the studies we've done show that there's no distinguishable difference between, say, looking at the effect of friction on a wave that travels from one junction to another, maybe 500 feet or 1,000 feet, as opposed to the method characteristics, which may make that calculation in 5 or 10 steps. Now, we do recommend that if you had a 50-mile long pipeline, that you don't put in a 50-mile long section. Well, I think we recommend that every 1,000 feet or so, we would suggest you put a node in, and you should have those in there anyhow to define the profile. So, I mean, I think if you took a 50-mile pipeline and you tried to model it in one step, and then you used a method characteristics where they have 1,000 interior nodes, yeah, you certainly could pick up a difference in the friction.
Okay. Is it okay to use Pipe 2010 surge for liquid hydrocarbon or crude oil?
Well, yes. So we part of the data is the viscosity of the fluid and the density of the fluid. So it is appropriate to use it for any liquid with where you know those properties. It should be a liquid though.
Do pressure sewer systems typically exhibit pressure surge?
Oh yeah, especially on so many of them have pumps that go on and off frequently, and there's a lot of problems that can occur if you're not looking at the surge. Surge is created when the pumps come on and off.
Okay, this one is from Stephen Haynes. I completed an analysis of a fire water system, sudden electric pump start, and found hardly any difference in peak pressures when the static or jockey pump pressure was varied. Traditional fire engineering says keep static and service pressure close together to avoid surges. The model seemed to say static pressure is a moot point. Would you have expected this?
I'd have to look at that more. I mean, I don't want to try to answer that. That's a little bit more complicated than I would like to take a crack at. So I do know Steve Haynes, and tell Steve
Steve,
hi,
you can send us the you can send us the model file.
But I'm not sure how. I wouldn't want to try to answer that without a little more in-depth look at it.
Okay. When specifying pipes and valves, say when we have a 10 bar at steady state, but max upsurge spike up to 16 bar G, do we need to specify pipes and pumps to PN16 to cover the spike, or PN10 will do, allowing only for steady state pressure? Okay.
Well, that's an engineering decision, and we don't try to make those at all. We provide the modeling advice, and so I would hesitate to try to answer that for one of our folks. So
okay.
I think that's about the best answer I can give.
Okay. Another from Bonnie. Can Pipe 2010 calculate the pump startup time? We have the motor torque speed curve and motor pump combined inertia data. Startup time.
I'd say we don't. No. We input the startup time. I mean, we can, it doesn't compute it from the it does the rundown time, the opposite for pump trips, but we don't have that capability for startup. No.
Okay. And so far, this is the last question, unless one pops up here in the next couple seconds. From Bill Levitt, you showed a bypass check valve around the pump to dissipate the surge. Why doesn't the surge just pass through the pump?
Well, the pump may have a check valve. It can. The pump may have a lot more resistance that you'd want in the bypass. The bypass might be a much lower resistance than the pump that's perhaps rotating, has stopped rotating or is rotating the other direction. So I think it's just a matter of being able to control it. I wouldn't want to count on the pump necessarily to do that.
Okay, I think that's everything. I guess we want to thank everybody for coming, and we'll have, that's the last question. We'll have additional webinars. We typically host one a month, and so look for those on our website. And thank you, Dr. Wood, very much. And thank you, Lisa, for hosting us. Dr. Wood, closing comments. Go ahead.
Well, I was thinking that anybody who has a suggestion, I've been thinking about webinars, and we could have an hour-long just quick training on how to build models, because we think the model building is very, very easy with Pipe 2000, Surge 2000. So if anyone has suggestions on what they'd like to see, to send them in to Lisa, and we'll, if we think that's something we can do, we may end up doing it. So anyhow, suggestions from folks would always be looked at.
Okay, I believe that concludes our meeting. Thank you, everyone, for attending, and please join us again soon in the future.